Okay, so hello. We're the mechatronics part of this project here. We're doing this RoboBoat competition with a couple of small caveats for our semester project. And I'm going to go ahead and introduce our team now. So my name is Alexander Croson. I'm a junior on my fourth years on so I'm a 5-year program. I'm a mechanical engineering major. I'm from Brussels, Belgium, and some activities that I do here is I'm on the school soccer team and I'm in the ROTC program. Some hobbies, I enjoy sports, I like traveling and I like fishing, and my career interests are undecided as of now.
So my name is Toby Smith. I am a junior studying mechanical engineering. I'm originally from Colorado Springs, Colorado. I play football here at Mines. Some of my hobbies are mountain biking, woodworking, and career interests, something in clean energy and manufacturing.
Hi, my name is Alec. I'm a junior here at Mines. I'm also studying mechanical engineering. I'm from Thornton, Colorado, and I compete on the football team here, and I'm a part of the National Society of Leadership and Success. Some of my hobbies are playing basketball, video games, and other outdoor activities. And my career interests have to do with designing and efficiency.
Hi, I'm Grant Smith. I'm a junior here studying mechanical engineering. I'm from Salina, Texas. I am on the football team here, and I am a member of the Hard Rocker Ally Association here on campus. Some of my hobbies include pretty much all sports, hunting, fishing, snowboarding, and I plan on going into the aerospace industry or the marine industry.
I'm Olivia Jones. I'm a junior mechanical engineering major from Avon, South Dakota. I'm on the women's track and field team. I'm the president of our student senate. I'm also a part of the International Society of Explosive Engineers, and I'm a part of WISE. Some of my hobbies are sports and traveling, and my career interests are mainly in the aerospace industry or semiconductor manufacturing.
Hi, my name is Drake Dittman. I'm a junior mechanical engineering major from Spearfish, South Dakota. Some of my activities at Mines, I help out on the Formula SAE team. My hobbies, I have a lot of, I like motorsport racing, doing things like snowboarding outside. I like working on cars, and I'm recently a cat dad. Some of my career interests, pretty much anything in the automotive or motorsport field, I'd be pretty happy with that.
So the competition that we were looking at is obviously it's a RoboBoat. It's held yearly. It's at an international competition in Daytona Beach where students go and design different types of autonomous surface vehicles. However, for our project, we decided to cut out the autonomous part and we just simply built an RC boat so that we can kind of use it as a base for the autonomous boat team. So some of the competition objectives, the original competition is building a fully autonomous surface vehicle to accomplish different tasks within a set test bed. So some of the 6 different tasks are mandatory navigation channel, the obstacle channel, the obstacle field, the acoustic docking, the object delivery, and the speed gate. This is kind of a sample of how the test bed would look like.
So for the mandatory navigation channel, this is going to be the first one that everyone must do in order to even attempt the other tasks. They have to start 6 feet behind the 2 sets of gates, and which are spaced pretty far apart, and they will have to go through them on their own and make it through them. For the obstacle channel, it's the same thing with sets of gates, but except they also have other obstacles. You can see that in the picture, the yellow dots. Those are the obstacles they have to avoid while going through all these gates. And for the obstacle field, they have to enter this and do a 360 around the buoy inside of the middle. And some of these other buoys on the outside will only have a 4 to 6 foot gap in between them. So it will have to configure the best route to enter and exit the obstacle field.
Another task that must be completed is the acoustic docking one. So out of 3 docks, one of them will play an acoustic sound that the ASV has to hear and then proceed to navigate and dock itself there. And then there will be a symbol corresponding to the docking bay to each one. And it has a certain mark on it, and that may be used for a task in another place. Another one is the object delivery. There's from that picture, you can see the 4 target areas. And here the teams can either use their boat or a UAV to deliver objects to the target area. And that can just be another level of how complicated they want to make it. If they want to actually have a UAV, because it has to deploy from the ASV. And then the last one is the speed gate. And it's pretty simple. It's pretty much just a down and back as fast as the boat can go. It just has to start between those 2 buoys, go around the mark, and then make its way back in the fastest amount of time possible.
The final task is the return to dock, and that could be after however many tasks each team wants to try to accomplish. It's pretty self-explanatory. It just has to return to dock. So the parameters for the RoboBoat competition, as you can see, the weight has to be under 140 pounds. And then the dimensions have to fit within a 3 foot by 3 foot by 6 foot box. For our kind of outcome that we want to accomplish for our semester project, we pretty much scaled our project down to fit within a 1 foot by 1 foot by 3 foot box, just because of the time limit that we have for our project. So our project statement, our goal with our given time limit this semester is to create a fully operational remote controlled boat by implementing our own mechatronic system of components. We look to the future for the potential that our model has for applications that could involve a fully autonomous submodel to compete in the RoboBoat competition. So this is our parts list. We are deciding to 3D print our hull and rudder. We have chosen a motor. We chose a brushed motor. We'll explain pretty much all of our parts further down the presentation. Our drive shaft with propeller. Our Bluetooth sensor is the HC05. Our servo metal gear digital RC servo motor is a high torque for pretty much any DIY application. And then we're also using Flex Seal to pretty much seal the bottom of our hull.
All right, so this is our initial design of the hull or the shell of the boat. This kind of doesn't accommodate what has to go into the boat. So that's when we started working on this design, which ended up being our final design. As you can see, it accommodates a piece that holds the motor in place so that the motor is able to drive the drive shaft. It also accommodates a piece that holds the servo, which will eventually control the rudder and steer the boat. So getting onto the specifications of the motor, the torque requirements are 0.65 Newton meters, and the power requirements are 7.2 volts. And the drive shaft with the propeller, this is 300 millimeters in length, stainless steel, and it is compatible with a DIY model.
So we're using a servo actuator to control the rudder of our boat. So it's just a metal gear with a dual ball bearing. a brush DC oarless motor inside. So this will be really fast, and it does support a voltage control, so we can do different speeds. So we will be using the ATmega 328P microcontroller. So we were given this as part of the assignment requirements, but to choose our microcontroller, we went through 5 different steps of deciding which one we needed, the number of input-output pins, the interfaces required, which was just the PWM for multiple different applications, memory requirements, processing speed, and the processing speed of the ATmega is a lot higher than, or a lot faster than we actually need, and then just the number of interrupts. So like we mentioned before, we're using the HC05 Bluetooth sensor. Some limitations with this is that it must be used with Android because of it uses Bluetooth 2.0 instead of iOS, which uses Bluetooth 5 or 4.0. So this will be one of the inputs to our microcontroller, and this will control the servo and the motor. So we are still working on our code, but this is a pretty rough flow chart of what we have. So just the Bluetooth input turns the motor on. Depending on which way the joystick is moved will determine how the servo turns the rudder so that the boat can move in that direction.
So this is our contact information. Our team lead was Olivia. If you have any questions, please let us know. We're here to answer them. If not, I think we're going to be followed by our RoboBoat competitive team.
So one quick question.
Yes.
Two quick questions. When designing your hull, were you looking at like how it does the displacement of water and all that to get some idea of both how well it's going to float, and then also whether the center of mass is low or high? And that second question, before you answer it, is going to factor into my second question. And my second question is, did you also consider, obviously in your final design, you realized, oh, we need to have a motor, we need to have the rudder. Did you consider that you also need to mount sensors and other things like that if somebody following you is going to be attempting to do the rest of the tasks in the challenge?
Yeah, so for us, we did talk about different designs of our boat. We had an initial design that we tried to see how it would float, and it was kind of canted to one side, so we had to redesign the entire hull. That's why we had a new design. We did talk about putting a certain amount of ballast in the boat. We haven't figured out exactly how much that is yet, because we still have to find out what our 3D printer is going to print our infill as, so we could see how much buoyancy the boat has. So after we get that, we're going to see how it floats and kind of decide where we want our center of mass to be on our new hull. But as for the second question, since we're mostly focusing on our an RC version of the boat, and they're focusing on the autonomous version, we hadn't even considered the where we put the sensors for if people wanted to pass and anything like that. We're just kind of laying the base for implementing mechatronic systems such as a motor or a servo into the hull.
Okay.
Yeah.
I only asked that last question because as a model, it may be less satisfying if you discover that your center of mass is too high if you start putting a whole bunch of sensors on it or some other. But that's also how you learn. So
we did also leave room in the bottom of the boat to kind of adjust using a trial and error method after we get into the water.
And so
Cool.
if that's all the questions you have for us, I think we're going to be followed up by our premier RoboBoat team. Yeah. Thank you for giving us your time.
Thank you.
no, thank you for the presentation. But yeah, good job.
Well, thank you, the